Okay, welcome to virtual GED class. Today we are going to be talking about the subject of probability, and it's our final class in this very long data analysis series we've been looking at. And again, data analysis is the type of math on the science, social studies, and math tests. And so we have been preparing for 3 tests at once. But I love the probability on the GED. Well, I love probability in general. I'm just a weirdo. Because what is probability? Probability is simply figuring out the likelihood of an event occurring, how likely something is to happen. And I think that's fun because I'm a game player and a card player, so figuring out the probability that I'm going to win pleases me. So that I like probability to begin with, but I like probability on the GED for another reason, because it's one of the few areas on the GED that they tend to keep the problems pretty simple. They don't get super complex. The math itself stays very simple, and we need that because there's a lot of complexity on the GED sometimes. And goodness, we needed some simple problems. So first of all, let's just define what probability is. Probability is a measure, so we're going to give it a number. And the measure is on a scale, and this is going to sound like a very small scale to you, of 0 to 1 of how likely something is to occur. So small scale starts at 0, goes to 1. 0 is the smallest your probability can be. So if I say that there's a 0 chance of something happening, well, that's not going to happen. Never going to happen. It's totally impossible. Whereas if I say that the chance is 1, that means it's always going to happen. It happens every time, 100% chance. So then I get students that get mad at me all the time because they're like, Kate, there are no numbers between 0 and 1. How can we use a scale of only 0 to 1? And I'm like, there's definitely numbers between 0 and 1. So help me out. We have GED students David here, and it looks like Veronica's joined us. Welcome, Veronica. I'm saying that there are numbers between 0 and 1. They definitely exist. What kind of numbers exist between 0 and 1? Any ideas? People tell me all the time there's nothing, and I say that's not true. Like I could have $0 or I could have $1, but I could have less, more than 0 and less than $1. Can you give me an example of a money amount that's more than nothing but less than $1?
25 cents.
Sure.
75 cents.
Sure.
80 cents.
Sure. Notice how I write these numbers. I write them with decimals.
Yeah.
There's other ways to write numbers like this. I could have less than a foot, but more than no measurement at all. I could have a half a foot, a quarter of a foot. So I could also express these numbers as fractions, proper fractions in this case, since they're going to be less than 1. And how else could we talk about pieces and parts of numbers? Well, we've been doing a data analysis series, and we've been learning to flip back and forth between decimals, fractions, and percents. So you could also see probability problems expressed as a percent. So I need a percent that's greater than 0 and less than 1. And students tell me a lot, like they forget what 1 means when it comes to percent. So if I say I have one whole thing, how much of a percent is that? You weren't with me the day we did intros to percents, were you, David?
No.
So one whole thing is the same as saying 100%. So it might seem really, really small to you to just say 1, but remember 1 and 100% mean the same thing. So there's a lot of percents between 0% and 100%. There's a lot of percents between 0 and 1, 27%, 49%. These could all be probabilities. So probabilities can be expressed as a decimal, a fraction, or a percent. In my college classes, I had to do it all 3 ways, but most commonly on the GED, I've seen it as a fraction or a percent. And so those are the 2 ways we're going to be looking at it today. So all of our answers will be either fractions or percents that are from that range from 0 to 1. They get no bigger than 1, no smaller than 0. So this is the last thing I want to say to you. I'm going to have a basic formula for you for probability, and you're going to see really quickly why this is going to get included in this unit because it looks really similar to finding a percent. Our basic formula for probability will be to make a ratio. Hey, that's a fraction of wins out of total. Oh my gosh, sounds super familiar. It's just a part to whole ratio like we did on ratio day. So we're just literally going to make a fraction, the winning outcomes to the total possible outcome. When I say wins out of total, I'll never say outcomes again, but that's what I'm talking about. Okay, now this is not a formula on your formula sheet. So you would need to remember that we are going to make a ratio of wins out of total. Now we'll get started. So here we go. Got some examples. Number 1 says a student spins the spinner below. What is the probability that the spinner lands on blue? The probability that the spinner lands on blue. Well, you can see this spinner here, and I've got some different spots, but only one of them is a winning spot. Only one of them is blue.
1 out of 8.
Exactly. 1 blue, that's a winning outcome out of 8 total possible outcomes. So I didn't count the others, I counted all of them. 1, 2, 3, 4, 5, 6, 7, 8. 1 out of 8 probability that the spinner lands on blue, and I'm literally done. And could it be this simple on the GED? It sure could. Yay. Yay for simple. Now here it is expressed as a fraction. You could also express it as a percent. And we can convert fractions to percent by hand, or we can do it in a calculator. We've been doing it in a calculator, so I'll just remind you guys. Now, I got to tell you, if it were me just doing this class for myself, I'd just leave it as 1/8 because it's easy, and I want my life to be easy, and I'm not trying to do more math. However, if this was on the GED and it was multiple choice answers, those multiple choice answers could be either fractions or percents. So I want you to know what to do if they're all percents and you've got it written as a fraction. Convert this to a percent in your calculator. You use the N/D button and you type 1 on the top of your fraction and 8 on the bottom. You literally then just arrow out of the fraction with the right arrow and press the convert to percent button. Now convert to percent looks like this. It's in green right above the closed parentheses. So in order to select it, you're going to need to press second. So second, convert to percent, and you can see that's the same as 12.5%. But both of these are totally correct answers, 1/8 and 12.5%. And I don't care which one you give me. And if you wanted to stop at 1/8, then you're a lazy mathematician like I am. David, you don't have a TI. And so you're at a disadvantage. You probably don't have a calculator with a convert to percent button. But I bet that you have a just a regular calculator or a phone calculator, yes?
Yeah.
You could very easily see what the percent is as well by just pressing the divide button. Remember that fraction bar means the same as divide. So 1 divided by 8 will convert it into a decimal. We see it's 0.125. And then you would just move it once, twice, and see 12.5%. So you could still convert it. It just takes a little more knowledge of decimals and percents.
Yep.
So let's look at number 2. Number 2 says, what is the percent chance that it lands on yellow? So I've given you a clue here that I do want my answer in a specific format. This time I've asked you for percent chance that it lands on yellow. So we will convert our final answer into a percent, but it's going to be pretty simple here. Let's take a look. So how many of these spaces are yellow?
It's 2 out of 8 or 1/4.
Exactly, 2 out of 8. And David obviously knows how to reduce fractions by hand, so he's seeing that 2 out of 8 is the same as 1/4. Now, whether you knew that or not, you don't have to know that to then convert that into a percent, because it won't matter if you type the 2 and the 8 or the 1 and the 4. You'll get the exact same answer. So I'm going to use the 2 and the 8, the original number, and then I'm going to convert into a percent by pressing second and the close parentheses button. And I can see that's the same as 25%. And I think most mathematicians have it memorized that 1/4 is 25%. So most of us don't need a calculator either way. But even if you don't have it memorized, that's okay. Now, let's see the next one. You're going to have to watch the wording. That's only how these problems could get tricky. The math doesn't really get too tricky usually on the GED, but the wording will. So like number 3 says, what is the probability that it doesn't land on yellow? That it doesn't land on yellow. So again, I'm going to make a fraction of my wins over my totals. In this case, the wins are when my spinner doesn't land on yellow. How many is that?
It's 6 over 8 or
exactly. This is not yellow, not yellow, not yellow, not yellow, not yellow, not yellow. I have 6 not yellow spaces out of 8 total spaces. And that one will reduce to 3 over 4. And again, your calculator will reduce. If you type in any fraction on your calculator and just simply press enter, it will automatically reduce it. So again, I'm going to use the N/D button to type in the fraction. I'll put 6 on the top, 8 on the bottom, hit enter, and it automatically reduces to 3/4. Now there's no indication here that they want a percent necessarily, but you sure could answer this as a percent. Another decent answer would be 75%. But those two answers are just as equally good as each other. I don't care which one you give. Let's move on. Let's get a little harder. Okay, here we go. A little more complex. So I'm going to remind you that last class when we were doing counting, if we had more than one event happen, we had to multiply each time there was a new event. Like, for example, if there were 6 possible ice cream flavors and 5 possible toppings and 3 types of sauces, then we would multiply in order to count how many total sundaes we could make. You remember that? So similarly, when we're doing probability, if we have multiple events happening, to find the probability of all those events happening, you multiply the probability of each individual event. So the probability, let's just write this down of what I said, of multiple events happening will be equal to the probability of first event times the probability of the second event times the probability of the third event, and so on and so forth. So what I'm telling you is if you have multiple events happening, you can just multiply together their probability to get the total. Wonderful, let's try it. So this says, what is the probability that you spin 2 green spins in a row, or you spin green 2 spins in a row? So I have 2 events happening. So I'm going to have to find the probability of that first event and the probability of the second event and multiply them together. So let's find the probability of the first event. What is the probability that I spin green on my first spin?
3 out of 8.
I absolutely agree. Now, what's the probability that I spin green on my second event?
Would it be 3 over 8 or 2 over 8?
Good question. So when I spin, does the first one go away?
Yes, because you already got it.
Yeah, so if I spin it, it's impossible to land on that space again?
No.
Oh, there we go. So it doesn't matter if I spun on that one green space before, it'll still be there next time. So it's still 3 over 8. But you're asking the exact right question, David, the exact right question, because some things don't replenish like that. For example, if I had a bag of marbles and I only had 3 green marbles and I reached and picked up a green marble and put it on the side, guess what? It wouldn't be there anymore.
Yeah.
But in the case of a spinner, it doesn't matter how many times I spin, my spinner doesn't change. So I'm going to multiply the probability of the first event with the probability of the second event. And remember, you can multiply fractions straight across. So it's 9 out of 64. But if you don't remember that, you could certainly use your calculator to do that. And again, all final fraction answers should be reduced. So if you're not very good at reducing fractions, you could type that in your calculator, 9 over 64, press enter, and you would see it would still give you 9 over 64 because that is a reduced fraction. And this is done. Now, I suppose I could convert this into a percent, but I don't even want to because dividing by 64, this is going to be so gross. Yeah, I get 14.0625%. Yeah, which is why I'm not even bothering to write a percent answer. Because I'm a mathematician, I like exact answers better than ugly rounded decimals. So then let's look at number 5. If you roll a single standard 6-sided die 3 times in a row, what is the probability of rolling an even number every time? So I have multiple events going on again. Do you see it?
Yeah.
How many events are happening here?
3.
3. So I'll have 3 probabilities multiplying together: the probability of the first event, the probability of the second event, and the probability of the third event. Okay, so I'm looking for what is the probability of rolling an even number every time. So the probability of rolling an even number. Well, let's just look at the first time. If you roll a 6-sided dice, what are your possible rolls?
3 out of 6.
David's already at the answer, but you could roll any number between 1 and 6. That's what a standard 6-sided dice has. And what he's noticing is that 3 of those numbers are even. 2, 4, and 6 are all even. So there's 3 even numbers out of 6 total possibilities. So now let's think about it. When you roll that dice, does it change the face of the dice? Will it be different the second time around, or will it be the same?
It'll be the same.
It'll be the same. So each one of these is going to be 3 out of 6, 3 out of 6, 3 out of 6. Now you can totally type this in with your calculator if you don't want to do this by hand, okay? 3 6 times 3 6 times 3 6. It'll do all the reducing for you and all the multiplying. But I'm a lazy mathematician. It's faster for me by hand. I know that 3 out of 6 is the same as 1/2, and it's super easy to multiply fractions. 1 times 1 times 1 is 1, and 2 times 2 times 2 is 8. I have a 1 out of 8 chance of rolling an even number every single time. Being good at reducing fractions and multiplying fractions makes these problems actually really, really simple. But even if you don't know how, your TI can do all of that. Very, very commonly, probability problems involve cards, dice, kind of game problems. So I have a problem here that involves a deck of cards. So it's going to require a little bit of background knowledge if you know what a deck of cards looks like. So it says, what is the probability to the nearest percent Ooh, a hint that they want a percent answer, of drawing a face card, a king, queen, or jack, from a standard deck of cards. Okay, so let's figure this out. How many kings are there in a deck of
4.
cards? Because we have the 4 suits, 1 heart, 1 diamonds, 1 clubs, 1 spades. And how many queens are there?
4.
4. And how many jacks are there?
4.
4. Wonderful. So if I'm looking to draw a face card could be a king, a queen, or a jack. So it looks like I have 12 winning cards.
Would you just add them together?
Yes, exactly. All those are wins. So I'm looking for wins, just like on the other page when we looked at the spinner, when we said we had a blue or a red. Well, there were 3 that were blue or red.
Okay.
Does that make sense?
Yeah. So 12 over 25.
I don't agree with the 25, and you might just have inverted numbers. Are you trying to remember how many cards are in a standard deck?
That's 52, isn't it?
It's 52, yeah. There's 13 of each suit, and there's 4 suits, and 4 times 13 is 52. So that is the prior knowledge you would need. You would need to either figure out how many cards are in a deck by counting, or you would have to know that there's 52 cards in a deck. Okay, now this fraction definitely reduces. I know it does because it's even over even, and all even numbers are divisible by 2. So there's a common factor in there, but I'm just going to use my calculator to reduce it for you guys who hate when I do fractions by hand. And 12 over 52 reduces to 3/13. Again, I could, I'm not done. Why am I not done?
Because you got to divide the 3 into 13 or 13 into 3.
Yeah, I wanted to leave it that way because I'm a lazy mathematician, but they forced me. They forced my hand when they said to the nearest percent. I have got to convert this to a percent.
So
Darn.
0.2307669.
Did you do the dividing? So David did the method where he just divides. So he got a decimal, 0.2307, yada, yada, yada. And then he said, I will convert that decimal into a percent by moving it once, twice. I get 23.07, yada, yada, yada percent. And now there's some rounding directions. To the nearest percent means I should let my number stop where? Okay, at the decimal place. Nearest percent works like a nearest whole number. So you're going to chop at the decimal place. We're going to call that about 23%. So if it says to the nearest percent, to the nearest foot, to the nearest yard, to the nearest inch, to the nearest person, bus, almost every to the nearest unit is chopping it off at the decimal place. The only exception I can think of to that rule is to the nearest cent, because this is how we talk about money. Take a look at that. We talk about money in terms of dollars, $24. And so if they said to the nearest cent, I would want 2 decimal places because we have 2 decimal places of our dollars or cents. So just to reiterate, the only time I can think of where when we say to the nearest unit, we're not talking about rounding at the decimals place, is to the nearest cent. Number 7 says a card is drawn from a standard deck and set aside. Then another card is drawn. What is the probability of drawing 2 face cards in a row from a, can you guys fix a typo? I meant to say from a standard deck. Okay, so now we have 2 events happening, don't we?
Yes.
First we draw a card, then we draw another card. Okay. Now I'm looking for the probability that we draw 2 face cards in a row from a standard deck. Now we already figured out the probability of drawing the first face card. It's 12 out of 52. We did that in the last problem.
Mm-hmm.
So I'm going to do that one pretty quickly. But then now let's talk about this one. They said the card is drawn from a standard deck and then it's set aside. Nobody put it back in the deck. So now what is going to be the probability that the next card we draw will be a face card? Well, we just set aside one of the face cards. We don't have 12 anymore. How many will we have now?
11.
11.
So
And again,
is it 51 now?
there you go. I set a card aside. I don't have 52 total cards anymore. I now have 51. And I'm going to go ahead and multiply this together in my calculator since these numbers are so big and would be challenging for most students to reduce. Again, I'm going to use the N over D button, and I get 12 over 52 times, and N over D again, 11 over 51. And my calculator gives me this ugly number, 11 over 221. Can you see how handy this calculator is since it does the fractions for us? Just about every problem on the GED that's a word problem, or whether it's a word problem, an algebra problem, or a geometry problem, you get this. So it's super useful. So number 8. A chocolate chip cookie factory has found that about 1 out of every 40 cookies they produce is completely devoid of chocolate chips. That is so sad, y'all. We could just mourn right here. If you reach into a bag of their cookies and randomly draw out 2 cookies in a row, what is the likelihood that both cookies will lack chocolate chips? Okay. Can you see that I have multiple events happening here?
Yeah.
How many events are occurring?
2.
2. So we'll have 2 probabilities. We'll multiply together. Okay, let's do the probability of the first. I'm going to reach into a bag and I'm going to pull out a cookie. What's the likelihood that it will not have chocolate chips? It will lack chocolate chips.
1 out of 40.
Yeah, 1 out of 40. They told me. Okay, now the question is, what's going to be the probability that the next cookie will also be devoid of chips? And we think that it's going to matter, but the fact is the machine behaves the way the machine is, no matter how many cookies we're drawing out. So you know what the probability is going to be for the next cookie? Still 1 out of 40.
Oh, 1 out of 40, yeah.
Yep, it's not going to change. It's just like that coin flipping. The machine always does 1 out of 40. The coin always has a 1 out of 2 shot. The dice always has a 1 out of 6 shot. What we do doesn't affect the die or the coin or the spinner or the machine. So 1 times 1 is 1, and 40 times 40 would just be 16 with 2 zeros on its butt. So I get a 1 out of 1600. And you could do it in your calculator if you don't like multiplying 40 by 40, but I'm too lazy to pick up a calculator. Are we good with that?
Yes.
And I don't want to put this as a percent because it would be ugly and they didn't make me, so I won't. See, I just try to convince you guys. Like half my life I spent trying to convince people they would actually like fractions if they just gave them a try.
Yeah, they're pretty easy.
I think so. For multiplying and dividing, they're a lot easier than decimals, actually. It's only for adding and subtracting that fractions are a pain. But you can see in probability problems, we're multiplying. So 9, a certain beach on the north shore of Oahu posts high surf advisories cautioning against swimming during 20% of the days of the winter season. If you go to the beach 4 days in a row this winter, what is the likelihood that a high surf advisory will be in effect every one of those 4 days? So again, I have multiple events going on. Do you see that, David?
Yeah.
How many events do I have going on?
Is it 4?
4, because I'm going 4 days in a row. So we're going to need the probability the first day, the second day, the third day, the fourth day. It's not written as a fraction. It's written as a percent this time. So I could come in here and put 20%, 20%, 20%, 20%. But what students do, I got to tell you, is when they write it as a percent, they make a really big error because then they come to their calculator and they write 20 times 20 times 20 times 20. And then they tell me, oh, it's 160,000%. And they're so proud of themselves. They're like, Kate, I remembered how to do probability. I'm so proud of me. 160,000%, which makes me giggle. Any ideas why this is a silly answer? We can't have a probability bigger than 100%. We said probability only goes from 0 to 1. So it's only going to go from 0% to 100%. So how can I have more than 100% chance?
Yeah, it's possible.
Okay, so this answer doesn't even make sense. So the problem is that they treated it like it's 20 times 20 times 20 times 20 when it's not. It's 20% times 20%. Say it again.
You got to convert it.
Yeah, you either have to convert it to a decimal or a fraction before you multiply it, or you have to type percent. Our calculator has a percent button, so you could use the percent button, but a lot of calculators don't. So I'll just convert it to a fraction since that's how we've been doing it. Literally, percent means out of 100. So that's 20 out of 100.
Or 2 out of 10.
Yes, it would be easier and faster to do 2 out of 10. You are reducing in your head. Actually. Or even better, 1 out of 5 if you can reduce in your head. But even if you were to type this into your calculator, you'd all get the same answer. But David, I'm super good at reducing in my head.
Yeah, me too.
Yeah, so I'll just go to 1 out of 5. So 1 times 1 times 1 times 1 is 1. And 5 times 5 times 5 times 5, let's see, 25 times 25, that's 625. Again, you can try to race me if you want by doing it in your calculator. But
you're probably quicker in your head.
Yeah, I am. I used to race my daughter while she was doing her calculus, doing it by hand. And if it's fractions, multiplying and dividing fractions, I'm almost always quicker in my head. But it's not because I'm some math ninja. It's just because fractions are really easy to multiply.
Yeah, they are.
Yeah. Okay. So that being said, I have a hint in this problem about what kind of final answer I expect. David, what do you think? What kind of final answer do you think I'm expecting?
A percent.
Yeah, absolutely. What in the problem made you think that? Veronica's never heard us talk about this kind of stuff before. What in that problem? They didn't specifically say, give me an answer as a percent. So how do you know?
They started with a percent.
We started with a percent. The likelihood is they want us to finish with a percent. So I am going to convert back from fraction form. Even if I had to convert into fractions to figure it out, I'm going to convert back. I'll do it the 1 divided by 625 way to get to a decimal. And then to convert into a percent, you just multiply it by 100, gain 2 decimal places worth of value, and it's a very small percent. It's 0.16%. So I told you guys that probability problems show up on the science and the social studies. And they do. I have a couple of science type examples. I could have just as easily done social studies type examples. It doesn't really matter. But when it's on the science and social studies test, it tends to have both passages and diagrams to accompany it. So now the probability isn't really that much harder, but what's harder is I'm distracting you with lots of words and lots of pictures. Okay, so let's take a look. Number 10 says, precipitation is defined as any product of the condensation of atmospheric water vapor that falls under gravity. That was a real life definition I got from Wikipedia, you guys. A meteorologist charted weather conditions at a certain locale each day for a year. He assigned a level to each weather condition and recorded the highest level reached each day. The results of his study are summarized in the table below. Based on the chart, what is the probability to the nearest percent that any given day in a year might experience precipitation? And then we have this chart here. And this is why probability comes up on the science test, because when you do a science experiment, it's really useful to know the likelihood that something is going to happen. That could be part of the results of your science experiment. Okay, so we're looking for the probability. What is the probability to the nearest percent? So we have a clue that they'd like it in percents, that any given day in a year might experience precipitation. So we're looking for the probability of precipitation, which means that we win if we have precipitation. So let's take a look at our chart here.
Are we going by a year for the number of days?
Yeah, I'm looking for clues in the passage to know the answer to that. I know the answer to that because I wrote it, but let's look at the passage. It says,
yeah, you're right. I see.
Recorded each day for a year.
Okay.
This table is representing 1 year.
5 out of 365.
I disagree, because we're looking for the chance that you might experience precipitation. It didn't precipitate 5 days. So I know you're thinking, but there's 5 kinds of precipitation. Yeah, no, but how many days out of the total days out of days, did we experience precipitation?
Oh, so you got to add up all the days that there was rain, snow.
Exactly, all the days that there were precipitation, and I defined what precipitation was for you in the passage. So take a look at this this table. Which one of these falls under that definition of precipitation? You're saying rain and snow. Are there any other ones that would be considered precipitation?
Sleet and hail.
Yeah, sleet and hail. They're all
There's 92.
water vapor coming down to earth. Now they might be frozen, they might be ice, they might be snow, they might be liquid, but they're all water vapor, condensing and coming down to earth. So very good. Good job interpreting your text. So all of these count as wins. So I'm going to add these up.
I think it was 92.
Oh, okay, you're on it.
I think.
And I'm going to write about this like a mathematician because I'm so stinking lazy. But it's going to be out of total days. Now, how many total days are there?
365.
Yeah, if you know that, you could just write 365 down there. What if you didn't know that? What could you do?
Google it.
You won't have Google on your math test. You could just add up all these days.
Add them all, couldn't you?
Yeah, exactly. Okay, so yeah, I get 92 out of 360. I love it. He's like, Google it. That's how I found out all the crap, Kate. Me too. Google's my best friend. Okay, 92 out of 365. Now, do I have any clues about what style answer they want, since there's multiple ways to answer probability questions?
Percent, the nearest percent.
Beautiful. So I will divide 92 divided by 365. And thank you for humoring me for asking the same questions again and again, David.
Yeah.
20. I get 0.2520, which is a decimal. And if I'd like to convert that into a percent, I jump once, twice, and I get 25.205, yada, 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 percent. And then do we have any rounding directions? Rounding is always the final thing you do. It says to the nearest tenth. So I'm going to chop it at the decimal. Yeah. And what will I get?
25%.
25%. Tells me that you're used to money, that you keep wanting to chop it after 2 decimal places. Because when we round to the nearest cent, we do keep 2 decimal places. Or do you handle money, or have you had a job where you handle money frequently?
Yeah.
Okay. So again, this problem was tricky, not because the math was any trickier too much, but more because I really hid numbers from you. I hid, you know, language, very typical of the science and the social studies. Okay, sweet. Let's look at the last one. Now, I gotta warn you, the last one I'm trying to blind you with language, okay? So just chill until we figure out what the question is before we decide to panic. Okay, ready? Here we go. This is so typical of the science test. I wouldn't be the least bit surprised if you have something almost exactly like this. They love the concept of heredity. So let's read this. Each part of the genetic code actually consists of two halves known as alleles. Offspring inherit one allele from each parent. When determining the probability of offspring inheriting certain genetic traits, scientists use capital letters to denote dominant alleles that code for traits that are always expressed. They use lowercase letters to denote recessive alleles that code for traits that can be carried in genes without being expressed. For an example, an individual might be heterozygous brown-eyed, meaning that their genes contain both an allele for brown eyes and an allele for blue eyes, but their eye color is brown. Two heterozygous albino rats, big A, little a, are mated. The recessive allele codes for grade coloring. Create a Punnett square to determine the possible phenotypes and genotypes of the offspring. Then answer the questions below. Okay, so looks really complex. A lot of complex science language that maybe we don't know. We talked about some of these vocabulary words last class, but we haven't really been doing science. And so we feel really overwhelmed. But the only thing you have to do here is know how to use a Punnett square. So we got a glimpse at one last time, but I'll just remind you that this is how a Punnett square looks. You just make a little square with the 4 individual boxes in it. And we're going to put the genotypes of the parents on the outside. And you put one parent along the top and one parent along the side. So let's look what we know about the parents here. It says 2 heterozygous albino rats, and they tell us what their genotypes are. Big A, little a are mated. So what they're telling us is both these parents are heterozygous albino rats. They both have this as their genotype, big A, little a. And I didn't have to understand a lot of this vocabulary because they put that right in the parentheses for me. So there it is. So I have the parents there. And then why do I do that way? Because, you know, if this parent has 2 different alleles, they could pass either one onto their offspring. There's a chance they could give them a big A dominant or a little a recessive gene. Either one could happen. And so that's why I want to account for both possibilities. And now we're going to treat it like a multiplication chart. We're just going to look at the cross. Like this one has a big A and another big A. So this offspring would have the genotype big A, big A. Okay. Now this next box, I see a big A from up top and a little a from on the left. So that offspring could have the genotype big A, little a. Then what would this next box be?
Big A, little a.
Exactly, a big A from this parent and a little a from that parent.
And then
this last one exactly would be 2 little a's. Okay.
So out of 4.
You end up with 4 possible genotypes. A big A, little a, or a little a, little a. But they code for different things. So what that reading was talking about when it was talking about dominant and recessive, the capital letter is always the dominant one. So if you have your genes code for both things, in this case, capital A is albino, and lowercase a is gray. So if your genes code for both things, the capital is going to win. So this rat, even though it had genes for both albino and gray, would end up albino. Now this guy only has albino, so he'll end up albino, but this guy only has gray, so he'll end up gray. The first question I have is, what is the probability that any offspring will have the genotype AA? So let's go back to our table here. How many of these guys have the genotype capital A, capital A?
1 out of 4.
1 out of 4. What is the probability that the offspring will have the genotype little a, little a? Well, I agree with you that one is 1 out of 4. There's only one little a, and so that'd be 1 out of 4, or 25%. What is the probability that any offspring will have the genotype big A, little a? Yes, there's 2 offspring that end up that way. So it's 2 out of 4, or 50%. So, you know, I mean, you could easily answer 1 out of 3 if you were looking at this list. So super important to look at the Punnett square itself. Okay, so we got A, B, and C. But now let's look at the albino or gray. So what is the probability that any offspring will be albino? Well, we said that obviously if their genes only code for albino, they'll be albino. So this first guy would be an albino. And then if they have both albino and a gray, the big letter is going to win. So this guy will end up albino as well. And so will this guy. So we end up with 3 out of 4 being actual albino rats. And by the way, guys, I have no idea if being albino actually goes with Mendelian genetics. I didn't even look it up. I just made up a question. Okay. And then, so what is the probability that any offspring will be gray? How many of these will actually end up being gray?
1 out of 4.
Only the guy who had 2 recessive gray genes will be gray, 1 out of 4, or that one would be, or 25%. That one would be, or 75%. You might be thinking, how's she doing the percent so quickly? In our intro to percent lesson, guys, we said you better know 1/4, 1/2, and 3/4. Nothing else. So I blinded you with language. Now the thing is I defined every new word I used in the reading, but it was so complex with so many new words that it would be really hard if this was the first time you were hearing all these words. It just would. Yeah. So even though I'm done with the math here, I'm just going to give a tip for anybody who hasn't taken a science test yet. I highly suggest you know some of these common heredity words, okay? So just take note of these if you don't know them. You should know what an allele is. You should know what it means to inherit. You should know dominant. You should know recessive. And knowing heterozygous. And I don't think I have the last word down here, but the last word would be homozygous. Would be super duper helpful for your science test, since they are just favorites of the GED test. One of the few subjects that I could say I am fairly certain you will definitely see on your science. Okay, so that would just be some good vocabulary to know. But I'm actually done. I'm done in under an hour. That's how simple the probability is on the GED. You know I usually talk for at least an hour and a half because I have too much to say. Okay. Thanks for joining me in class this week. I will see you in our next class. I don't know what we're doing in our next class because this was the final data analysis unit. I'm taking the month of July off to plan that. So we'll be back in August with a whole new unit. All right. Thanks for joining me.